Hello everyone, we are Team Base and we are trying to address the problem of employee attrition, which is amongst the major issues daunting the HR department of every organization. The project is focused on Bayesian logistic regression on an IBM employee attrition dataset. The dataset has 1470 observations and 35 features. We have a classification problem with a binary target variable attrition with two levels. Yes, where the employee leaves the company, and no, where the employee stays with the company. Therefore, we have used a logistic regression model. We will try to address two issues here: a prediction model to predict which employee is likely to leave the organization, and the second, which factors contribute to employee attrition rate. We have used Bayesian analysis to develop a prediction model as opposed to classical analysis because Bayesian analysis estimates a fixed value for model parameters. Bayesian analysis quantifies uncertainty when analyzing employee attrition. Here in the following diagram, we have plotted a attrition variable where we can see that it is quite unbalanced where no dominates yes. Here we have taken two variables over time and years in current role. These two variables are compared with attrition and we have plotted two graphs. Here we can see people who have worked overtime have a more attrition rate than people who don't work overtime. In the next figure, we have also computed Pearson's correlation coefficient to measure the correlation between the independent variables. On seeing the Pearson correlation matrix, we can see that monthly income and job level have a high correlation. Hence, we have opted to drop monthly income and also percent salary hike income for the same reason. We have also dropped a few other columns like employee count over 18, standard hours, and employee number since it has only one value like a ID.
We have taken up a logistic regression model with attrition, that is the target variable, which has a Bernoulli distribution with mu parameter to create a prediction model. Mu is a function of beta estimates which act as the slope of independent variables, which creates an impact on the target variable, and the beta parameter follows normal distribution with mean and its standard deviation. Since the relationship between model parameters, that is the independent variables, and target variables is not linear, we have taken log of the mu equation. We have opted for a standardized model where we have divided it by standard deviation of the variables. We have taken non-informative prior approach of Bayesian analysis. To achieve a prediction model with better recall, we have first done a sample check by randomly choosing 150 observations to get an idea about a good combination of MCMC settings. Then we have taken constant burning steps as 1000 and adapt steps as 1500 in all the models. We have tried three different combinations or three different models of MCMC settings by changing the number of thinning steps and the safe steps to reduce the autocorrelation in our model. Our most efficient model till date has taken 3 end chains and 15 thinning steps and 2000 safe steps. We have randomly chosen beta 16 MCMC setting results to display the improvement in the models over the different combinations. We can see that in the first model, even though the chains converge in the trace plot over the iterations for beta 16 parameter, which is work life balance variable, ESS is relatively low as 1500 and but shows high correlation over the iterations. In the model 2, we can see that the ESS, which is 1700, and autocorrelation has been improved by increasing the number of thinning steps to 25 with a much lower MCSE of 0.009. But the shrink factor shows a lot of variation over the iterations but is still below 1.2. In a final model 3, we have achieved a relatively low autocorrelation with low MCSC of 0.02. The density plot shows overlapping chains, and the HDI are approximately overlapping too in the density plot. The shrink factor is close to 1 eventually, and our chains have converged in the trace plot. We are focusing on autocorrelation in MCMC settings because high autocorrelation produces clumsy and unrepresentative results of the true posterior distribution. The figure shows posterior distribution for a beta 16 parameter, which is work-life balance, with 95% HDI limits of minus 3.13 and 1.71, and with the mode that is the beta value in the prediction model as minus 0.498, along with the beta values for other variables like years in current role and training times last year. Since the beta 16 value, the 95% HDI has 0 in it, it gives us an opportunity to improve our model recall by feature selection, which is one of the advantages of using Bayesian analysis. We can see that the recall is really low for the model, which calls for improvement as given in the confusion matrix. We also plan to use A/B testing in our model to achieve better results.